In this section, we're going to look at the optimization process under SUSE Linux Enterprise. Optimization is usually performed by an iterative process. In other words, we go through the work of gathering information, then analyzing the various subsystems, and then tuning those subsystems based on what our goals are. And then we watch to make sure that those changes accomplish what it is that we want or are moving us in the direction we want. We then go through the process again iteratively, in order to further improve based on, again, our overall design goals. So over and over, we work through this process in order to improve the way that the system performs. So in order for this to work, though, we need to use specific tools in order to work with and push through these iterations as we improve the system. And one of the primary packages for doing that is the Systat package. Now, this is an interesting package because it contains benchmarking and performance data capturing tools from everything from the hard drive to memory and throughput and all sorts of things. And so Systat contains SAR, SADC, SA1, and SA2, which are very useful for tracking information, SADF for space. You've got your IOStat tools, MPStats, and ISAG. So Systat brings with it a bunch of tools that will be of value when iterating through the optimization process. So what are those various tools that we mentioned? Well, SAR collects and saves information specific to the system. In other words, in order to track what is happening on a machine, something has to be recording it. SAR is designed specifically to capture that kind of information. There's also the System Activity Data Collector, the SADC. SA1 and SA2, although very similarly named, one of them collects information for you to track and to gather, and SA2 will write that information to a report. So one is for the collection and one is for the summarizing and export or dumping that information for consumption. SADF gives you information for database loading or graphing. You also have IOStat, which is great for CPU statistics, IO statistics based on devices, partitions, and then even network file systems can be tracked through that. You also have the MPStat command and the ISAG. MPStat reports individual or combined processor-related statistics. So how's the CPU actually functioning? And ISAG is an interactive grapher, allowing you to create visualizations of how performance is being collected performance data is being collected by SAR. So there's also the sysctl command. Sysctl is useful because it gives you the ability to tune kernel parameters at runtime. And so you can use it in a dynamic method, and usually this is an exploratory type method where you want to see what the impact of a change is on a system, but you don't want it to be permanent. So you use it as a dynamic, so it looks at the changes, and then you gather information and then analyze it to see if that's what you want. But then, of course, you can also use sysctl to set it as a static thing so that the next time that the system is restarted, that machine will inherit those changes that you've defined as well. Now, what other tools do you have out there? Well, we've looked at SAR and the tools there, but there's TOP as well, which we've kind of mentioned before, but TOP is very important because it is, for a lot of administrators, it is the first tool that will be cracked open when looking at what's going on with the system, for good reason. It kind of has a dashboard. It tells you what the CPU's been doing, the load values. You can see what memory's doing, how much swap is being consumed. And you can track individual applications to see what they're doing as well. So there's a lot of information that can be gathered here as well. Now, IOTop is similar to TOP in what it's trying to accomplish, but zeroing in on input-output or disk I/O and reports information. There's an IFTop, which is specific to network traffic, again, giving you information specific to network interfaces and something similar to the TOP interface, not identical, but does give you some commonality. There's also other tools that you'll use when doing analysis, specifically strace. strace is great for seeing how an application is interacting with the system. strace allows you to basically structure an application. What is an application doing? How is it interacting with the system? And where can improvements be made? strace is used frequently by application developers when they're trying to track why an application is doing something. But of course, this also falls into an administrator's lap as well, so that they can say, why is an application causing issues on my system? Where are the bottlenecks here? And so very useful for tracking information. You can use various settings. The -C option is an example to get the count time, the number of errors, the number of calls that are being executed. And you can use a verbose mode, and of course you can dump that to a file and track that information for later consumption as well. strace is typically used to determine if the blocking factor for a disk I/O is a particular application. And it's also, of course, can be used to track memory information, how much memory allocation is being done. In other words, you will see a lot of strace when we have, if you're tracking memory leaks, that could be a reason to have it, as well as many other things. But strace has a lot of functionality and a lot of use cases, especially when optimizing. You can start tracing after an application, so you don't have to start the application with strace. You just find the process ID of that application and then use the strace command with the -P and the process ID, and it will track that application in order to see what's going on. Obviously, since you're tracking an application and viewing how it's using and talking to not only memory but other system resources, you need to run it as root in order to be effective.